Hi, I'm Bob. In this last episode of the Introductory Econometrics course, I will solve the problems and computer exercises for Chapter 12. I use the textbook Introductory Econometrics, a modern approach, the 7th edition by Professor Jeffrey Wooldridge for this course. You can download the textbook datasets from the link below for the computer exercises. Remember to subscribe to my YouTube channel if the solutions help, and continue to watch videos for other courses. Let's see problem 1. When the errors in a regression model have AR1 serial correlation, why do the OLS standard errors tend to underestimate the sampling variation in the beta? Is it always true that the OLS standard errors are too small? We consider the variance of the OLS slope estimator in the simple regression model. We assume the sample average of the x is 0. The OLS estimator beta1 hat can be written as follows, as 12.3 in the textbook. The actual variance of beta1 hat is 12.4 in the textbook. The OLS variance without autocorrelation is its first part. In most cases, the second part is positive, so the actual variance is greater than the OLS variance. In other words, the OLS standard error tends to underestimate the actual standard error. But it is not always true, because the second part could be negative in some cases. Let's look at the second problem. Explain why it's wrong with the following statement. The Cochrane-Orcutt and Prais-Winsten methods are both used to obtain valid standard errors for the OLS estimates when there is a serial correlation. The statement is false. The valid standard errors for the OLS estimates when there is a serial correlation are called heteroscedasticity and autocorrelation consistent HAC standard errors. The Newey West standard errors are one of them. The Cochrane-Orcutt and the Prais-Winsten methods are the feasible GLS procedures to correct for AR1 serial correlation. They involve quasi-differenced transformation. Let's solve problem 3. In example 10.6, we use the data in FAIR to estimate a variant on FAIR's model for predicting presidential election outcomes in the United States. For part 1, what argument can be made for the error term in this equation being serially uncorrelated? Because U.S. presidential elections occur only every 4 years, it is reasonable to assume that the error term is serially uncorrelated. In part 2, when the OLS residuals from 10.23 are regressed on the lagged residuals, we obtain rho hat equals minus 0.068 and standard error equals 0.240. What do you conclude about serial correlation in the mu-t? The null hypothesis is rho equals 0. The t-statistic for the null hypothesis is minus 0.068 divided by 0.240, which is minus 0.28. Its p-value against a one-sided alternative is 0.4. We fail to reject the null hypothesis that there is no serial correlation. In part 3, does the small sample size in this application worry you in testing for serial correlation? The test for serial correlation is asymptotically valid. That is, the t-statistics are valid as the sample size approaches infinity. The small sample size is a concern, but the estimate of rho is very close to 0, so I don't worry about the no serial correlation conclusion. Let's go to problem 4. True or false? If the errors in a regression model contain arch, they must be serially correlated. The statement is false. Take the simple regression model as an example. To test for autoregressive conditional heteroscedasticity arch, we regress the squared residual in time t on time t minus 1. If the error term contains autoregressive conditional heteroscedasticity arch, the slope coefficient alpha 1 is significantly non-zero. But to test for autoregressive process or serial correlation AR, we regress residual in time t on time t minus 1 and check rho 1. Example 12.9 in the textbook is a case where the error term contains arch but not AR. Let's solve problem 5. In part 1, in the enterprise zone event study in computer exercise C5 in chapter 10, a regression of the OLS residuals on the lagged residuals produces rho equals 0.841 and standard error equals 0.053. What implications does this have for OLS? The t-statistics is (15.9), which is high enough to reject the null hypothesis of no serial correlation of the error term. With serial correlation, the OLS standard errors are very likely to underestimate the true standard errors. The t-statistics for beta hats are higher than the true ones, and the estimates are more statistically significant than they actually are as a result. In part 2, if you want to use OLS but also want to obtain a valid standard error for the enterprise zone coefficient, what would you do? We can use heteroscedasticity and autocorrelation consistent standard errors, HAC standard errors, such as Newey West standard errors. Let's find answers to problem 6. In example 12.8, we found evidence of heteroscedasticity in multi in equation 12.47. Thus, we compute the heteroscedasticity robust standard errors along with the usual standard errors. What does using the heteroscedasticity robust t-statistic do to the significance of return in time t-1? With the heteroscedasticity robust standard error, the t-statistic is 0.86. It is small, and its one-sided p-value is 0.2. We could not reject the null hypothesis that the past return does not help predict the future return, or the efficient markets hypothesis. Let's do problem 7. Consider a standard multiple linear regression model with time series data. Assume that assumption ts.1 to ts.4 holds. In part 1, suppose we think that the errors μt follow an AR1 model with parameter ρ, so we apply the Prais-Winsten method. If the errors do not follow a AR1 model, for example, suppose they follow a AR2 model or a MA1 model, why will the usual Prais-Winsten standard errors be incorrect? In the Prais-Winsten method, the quasi-differenced transformation is based on AR1 errors. Consider a simple regression model. The transformed regression model is serially uncorrelated only when the error term μt in the original model follows a AR1 process. If μt does not follow an AR1 process, the error term et in the transformed regression model could be serially correlated, and the standard errors for the coefficients are incorrect. In part 2, can you think of a way to use the Newey-West procedure in conjunction with Prais-Winsten estimation to obtain valid standard errors? Be very specific about the steps you would follow. The way to use the Newey-West procedure with Prais-Winsten estimation has 3 steps. In step 1, run the OLS regression of yt on xt and obtain the OLS residuals μt hat. In step 2, run the OLS regression of μt on μt-1 and obtain ρ hat. In step 3, we perform the Prais-Winsten transformation and run the regression of yt tilde on xt tilde with Newey-West standard errors. In the last step, the error term in the transformed equation may be serially correlated, so we use the heteroscedasticity and autocorrelation consistent HAC standard errors that are robust to serial correlation. In part 3, explain why your answer to part 2 should not change if we drop assumption ts.4. If we drop the homoscedasticity assumption ts.4, the answer to part 2 should not change because the Newey-West standard errors are robust to both heteroscedasticity and autocorrelation. They are also called heteroscedasticity and autocorrelation consistent standard errors. Let's find answers to problem 8. Suppose in a static or distributed lag time series correlation, you can use n equals 280 quarterly observations. What would be some reasonable value for the lag g in the Newey-West estimator? With a sample size of 280, we can calculate the lag g using several methods recommended in the textbook. One is to take the integer part of n to the power 1/4, which is 4. Another 2 methods give the lag G equal to 4 or 5. Let's continue our solutions to computer exercise for Chapter 12. Let's turn to the computer exercise for Chapter 12. As usual, I use data to solve all the computer exercises. Computer exercise 1 is about the serial correlation in the error terms. In example 11.6, we estimated a finite distributed lag model in the first differences. Use the data to test whether there is a AR1 serial correlation in the errors. We run the regression first. And then we store the residuals using the predict command in Stata. After that, we generate the lagged residuals. To test for the AR1 serial correlation, we regress the residuals on the lagged terms and find that the slope coefficient ρ is statistically significant at the 5% level. The residuals are positively correlated. Although we use the differenced data in the regression model, the residuals still have AR1 serial correlation. Let's do computer exercise 2. In part 1, estimate the distributed lag model from problem 5 in chapter 11. Use regression 12.20 to test for AR1 serial correlation. We first run the distributed lag model. Then we store the residuals and generate the lagged residuals. Finally, we regress the residuals on the lag terms and find that the slope coefficient ρ is statistically significantly different from 0 at the 1% level. So we conclude that the error term in the model has a AR1 serial correlation. In part 2, we estimate the model using iterated Cochrane-Orcutt estimation. What is your new estimate of the long-run propensity? We first estimate the model using OLS. To find the long-run propensity, we can estimate the modified equation. The coefficient on the wage growth is the long-run propensity. It is 1.17. Now we re-estimate the model using iterated Cochrane-Orcutt estimation. We first declare the time series data and then use the Prais command to estimate the model. The option CORC means the Cochrane-Orcutt transformation. The new estimate of the long-run propensity is 1.11. In part 3, using iterated Cochrane-Orcutt, find the standard error for the long-run propensity. Determine whether the estimated long-run propensity is statistically different from 1 at the 5% level. The standard error is 0.191. The t-statistic for the null hypothesis is 0.58, and its p-value against a two-sided alternative is 0.57. We could not reject the null hypothesis at any reasonable level. The long-run propensity is not statistically different from 1 at the 5% level. Let's find answers to computer exercise 3. In Part 1 of Computer Exercise C6 in Chapter 11, you were asked to estimate the accelerator model for infantry investment. Test this equation for AR1 serial correlation. We first estimate the accelerator model, and then we store the residuals and generate the first leg term. We regress the residuals on its first leg and find that the slope coefficient is not statistically significant at any conventional level. There is no evidence of AR1 serial correlation. In Part 2, if you find evidence of serial correlation, we'll estimate the equation by Cochrane-Orcutt and compare the results. Since we find no evidence of serial correlation, there's no need to use feasible GLS methods, such as Cochrane-Orcutt or Prais-Winsten estimation. Let's solve computer exercise 4. In Part 1, estimate equation 12.48. Let ht hat be the fit values from this equation. How many ht hat are negative? We regress the variable return on the leg return and store the residuals. After generating the squared residuals, we run the conditional variance equation, that is, regress the squared residuals on the leg return. To store the fitted conditional variance, we use the predict command with the xb option. We name the fit value h hat. We find that out of the 689 observations in the model, 12 fitted conditional variances are negative. In Part 2, add return squared to 12.48 and again compute the fitted values ht hat. Are any ht hat negative? We generate the squared return and add it to the conditional variance model. Now the variance is a quadratic function of past returns. There is no fitted values below 0. In Part 3, use the ht hat from Part 2 to estimate 12.47 by weighted least squares. Estimate of beta 1 with that in equation 11.16. Test the null hypothesis beta 1 equals 0 and compare the outcome when OLS is used. H is a function of the past returns. We use h to construct the transformed equation. We divide the original variables by the squared root of h. Using the transformed variables, we find that t statistic is 1.06 and beta 1 is not statistically significant at the 10% level. It is less significant than the OLS estimation. In Part 4, estimate 12.47 by weighted least squares, using the estimated arch model in 12.51 to obtain the HT hat. Does this change your findings from Part 3? We estimate the arch model to obtain HT hat. Using the new HT hat to do the weighted least squares estimation, we find that beta 1 is still not statistically significant, with an even lower t-statistic of 0.51. Let's do computer exercise 5. Consider the version of Fair's model in example 10.6. Now, rather than predicting the proportion of the two-party vote received by the Democrats, estimate a linear probability model for whether or not the Democrat wins. In Part 1, use the binary variable Dem wins in place of Dem vote in 10.23 and report the results in standard form. Which factors affect the probability of winning? Use the data only through 1992. The linear probability model shows that only the incumbent is statistically significant at the 5% level. The other three variables are statistically insignificant at the 10% level. Whether the candidate is incumbent affects the probability of winning. In Part 2, how many fit values are less than 0? How many are greater than 1? We use the predict command to generate the fit values. 2 fit values are less than 0 and 2 are greater than 1. In Part 3, use the following prediction rule. If the fit value is greater than 0.5, you predict the Democrat wins. Otherwise, the Republican wins. Using this rule, determine how many of the 20 elections are correctly predicted by the model. We define a new dummy variable, DevWin2. It equals 1 if the fit value is greater than 0.5. Then we compare the prediction with the true outcome. The model correctly predicts 15 out of 20 elections. In Part 4, plug in the values of the explanatory variables for 1996. What is the predicted probability that Clinton would win the election? Clinton did win. Did you get the correct prediction? We plug in the values of the explanatory variables for the year 1996. The predicted winning probability is 0.55. It is above 0.5. According to the prediction rule, we get the correct prediction. In Part 5, use a heteroscedasticity robust t-test for AR1 serial correlation in the errors. What do you find? We regress the residuals on the lagged residuals. The heteroscedasticity robust t-statistic for the slope coefficient is minus 0.80. We find no evidence of an AR1 serial correlation in the error term. In Part 6, obtain the heteroscedasticity robust standard errors for the estimates in Part 1. Are there notable changes in any t-statistics? We estimate the model using the heteroscedasticity robust standard errors. And the usual standard errors, and then compare the estimates in a table. We find no substantial changes. Let's solve computer exercise 6. In Part 1, in computer exercise C7 in Chapter 10, you estimated a simple relationship between consumption growth and growth in disposable income. Test the equation for AR1 serial correlation. We run the regression model and store the residuals using the predict command with the residual option. Then we generate the lagged residuals. The AR1 regression shows no evidence of first-order serial correlation in the errors. In Part 2, in computer exercise C7 in Chapter 11, you tested the permanent income hypothesis, the growth in consumption on its leg. After running this regression, test for heteroscedasticity by regressing the squared residuals on consumption growth at t-1 and its squared term. What do you conclude? To test the permanent income hypothesis, we regress consumption growth on its leg. To test for heteroscedasticity in the errors, we store the residual and generate its square term. Then we regress the squared residuals on the lagged consumption growth and the squared lagged consumption growth. The F statistic for the joint significance is 1.08 and its p-value is 0.35. So there's no evidence of heteroscedasticity in the errors. Let's go to computer exercise 7. Obtain the iterative Cochrane-Orcutt estimates for example 12.4 and compare them with the Prais-Winsten estimates. We can estimate the model by OLS. Cochrane-Orcutt and Prais-Winsten, and then compare the estimates in a table using Stata's stab command. The Cochrane-Orcutt and Prais-Winsten estimates are similar. They are both feasible FGLS estimations. The former does not use the first observation while the latter does. They are asymptotically the same. Let's solve computer exercise 8. In Part 1, run an OLS regression of percentage of fatal accidents on a linear time trend monthly dummy variables and the following variables. Test the errors for AR1 serial correlation using the regression in equation 12.20. Does it make sense to use the test that assumes strict exogeneity of the regressors? To test the errors for AR1 serial correlation, we regress the residuals on the first leg residuals. The estimate for the slope coefficient ρ is positive and statistically significantly different from 0 at the 1% level. The t-statistic is 2.99. It is reasonable to assume straight exogeneity of the regressors because after controlling for the time trend, seasonality, employment, and the two law variables, the unobserved factors in the error term that affect the fatal accidence rate should not be correlated with the explanatory variables. Impact 2. Obtain serial correlation and heteroscedasticity robust standard errors for the coefficients on the two policy variables, using 4 legs in the Newey West estimator. How does this affect the statistical significance of the two policy variables? We estimate the model by OLS with Newey West standard errors and usual standard errors and then compare the estimates in a table. The Newey West standard errors are larger than the usual standard errors. The statistical significance of the speed law variable becomes lower using the Newey West standard errors, but it is still statistically significant at the 5% level. The seatbelt law variables is statistically insignificant in both cases. Impact 3. Estimate the model using iterative Prais-Winsten and compare the estimates with the OLS estimates. Are there important changes in the policy variable coefficients or their statistical significance? After using the Prais-Winsten estimation, we compare the estimates with the OLS estimates. We find no substantial changes. The coefficient on the speed law variable is slightly smaller, and its standard error is slightly larger, but it is still statistically significant at the 5% level. The effect of the seatbelt law is still statistically insignificant. Let's find answers to computer exercise 9. The file fish contains 97 daily price and quantity observations on fish price at the fish market in New York City. Use the variable log average price as the dependent variable. In part 1, regress the log average price on 4 daily dummy variables with Friday as the base. Include a linear time trend. Is there evidence that price varies systematically within a week? We regress the variable log average price on the time trend and the 4 daily dummy variables with Friday as the base. We find that the 4 daily dummy variables are individually and jointly insignificant at any reasonable level. There is no evidence that fish price varies systematically within a week. In part 2, add the variables wave 2 and wave 3 which are measures of wave heights over the past several days. Are these variables individually significant? Describe a mechanism by which stormy seas would increase the price of fish. The two wave variables are individually significant. The increase in the cost of fishing shifts the supply curve to the left, resulting in a rise in the fish price, assuming that the demand for fish is not affected by the wave heights. Impact 3. What happened to the time trend when wave 2 and wave 3 were added to the regression? What must be going on? The time trend becomes statistically insignificant after adding the two wave variables. Notice that the time trend has a negative effect on the fish price in the original model, so the waves must become increasingly lower over time. The wave variables absorb the negative time effect, making the time trend insignificant. We can confirm it by regressing the wave variables on the time trend. Impact 4. Explain why all explanatory variables in the regression are safely assumed to be strictly exogenous. The time trend, the daily dummy variables, and the height of the waves are not determined by any factors that affect the fish price. They should be exogenous. Impact 5. Test the errors for AR1 serial correlation. After declaring the time series data using the tsset command, we can use the L dot operator to indicate the lag of the variable. We find evidence of a positive AR1 serial correlation in the error term. Impact 6. Obtain the Newey West standard errors using 4 legs. What happens to the t-statistics on wave 2 and wave 3? Did you expect a bigger or smaller change compared with the usual OLS t-statistics? Usually, the Newey West standard errors are larger than the usual OLS standard errors. We find that the Newey West standard errors for wave 2 and wave 3 are similar to the usual OLS standard errors, making the t-statistics change little. The statistical significance is unchanged. Impact 7. Obtain the Prais-Winsten estimates for the model estimated impact 2. Are wave 2 and wave 3 jointly statistically significant? We estimate the model with the Prais-Winsten transform method for AR1 errors. The estimates for the coefficients on both wave variables reduce, but they are still statistically significant, and they are jointly significant at the 1% level, according to the F test. Let's do computer exercise 10. In part 1, using the entire data set, estimate the static Phillips curve equation by OLS and report the results in the usual form. Impact 2. Obtain the OLS residuals from part 1 and obtain rho from the regression mu t hat on mu t minus 1 hat. Is there strong evidence of serial correlation? Yes, there's strong evidence of serial correlation. Impact 3. Estimate the static Phillips curve model by iterative Prais-Winsten. Compare the estimate of beta 1 with that obtained in table 12.2. Is there much difference in the estimate when the later years are added? We estimate the static Phillips curve by the iterative Prais-Winsten method. Here are the estimates along with the OLS results in a table. Compared to table 12.1 in the textbook, the estimate of beta 1 does not substantially change. Impact 4. Rather than using Prais-Winsten, using iterative Cochrane-Orcutt, how similar are the final estimates of rho? How similar are the PW and CO estimates of beta 1? The Cochrane-Orcutt method does not use the first observation while the Prais-Winsten method does, but they are asymptotically the same. The rho in the Prais-Winsten is 0.789 and the rho in the Cochrane-Orcutt is 0.782. The estimated trade-off effect between inflation and unemployment is smaller using the Cochrane-Orcutt estimation. Let's look at computer exercise 11. In part 1, estimate the model in equation 12.47 and obtain the squared OLS residuals. Find the average, minimum, and maximum values of mu t squared hat over the sample. We regress return on its first leg. Then we store the residuals using the predict command with the residual option. After that, we generate the squared residuals. We name it mu hat squared. Finally, we find the average, minimum, and maximum values of mu hat squared using the summarize command. Impact 2. Use the squared OLS residuals to estimate the following model of heteroscedasticity. Report the estimated coefficients, the standard errors, the R squared, and the adjusted R squared. Impact 3. Sketch the conditional variance as a function of the lagged return. For what value of the lagged return is the variance the smallest, and what is the variance? We can use the graph two-way function command to draw the curve. It is U-shape. The squared residuals are smaller when the lagged returns are smaller. The squared residuals are estimates of the variance of return. The variance is the smallest when lagged return equals 1.33. The smallest variance is 2.73. Impact 4. For predicting the dynamic variance, does the model Impact 2 produce any negative variance estimates? No, the predicted values are all positive. We can confirm it either by looking at the graph in part 3 or summarizing the predicted values. In part 5, does the model in part 2 seem to fit better or worse than the Arch 1 model in example 12.9? Explain. The R-squared and the adjusted R-squared are 0.1303 and 0.1278 for the model in part 2, and they are 0.1136 and 0.1123 for the Arch 1 model. The former fits the data better than the latter. In part 6, we add the second leg to the Arch 1 regression in equation 12.51. Does this leg seem important? Does the Arch 2 model fit better than the model in part 2? The second leg of the squared residuals is not statistically significant at the 10% level. The coefficient is also tiny, so it is not important. The adjusted R-squared is 0.1125, which is still lower than that from the model in part 2. Notice that we can use the capital dot and capital 2 dot operators after declaring the time series data with the tsset command. Let's go to computer exercise 12. In part 1, obtain the OLS residuals from the accelerator model and use the regression mu hat t on mu hat t minus 1 to test for serial correlation. What is the estimate of rho? How big a problem does serial correlation seem to be? The AR1 model for the residuals shows little evidence of AR1 serial correlation in the errors. In part 2, estimate the accelerator model by the Prais-Winsten method and compare the estimate of beta 1 to the OLS estimate. Why do you expect them to be similar? The Prais-Winsten estimation is a feasible GLS method for AR1 serially correlated errors. Since there's little evidence of serial correlation in the errors, the estimates are similar to the OLS estimates. Let's solve computer exercise 13. In part 1, estimate the equation and test the errors for AR1 serial correlation without assuming unemployment is strictly exogenous. What do you conclude? Without assuming strictly exogenous unemployment change, we can include the unemployment change in the AR1 model as a control. The model gives a statistically insignificant estimate of rho. There is little evidence of serial correlation in the errors from the original model. In part 2, regress the squared residuals on unemployment change. What do you conclude? we regress squared residuals on unemployment change and find that the slope estimate is statistically significant at the 5% level. There is evidence of heteroscedasticity in the errors of the original model. The error variance increases with the unemployment change. In part 3, obtain the heteroscedasticity robust standard error for the OLS estimate beta 1. Is it substantially different from the usual OLS standard error? The heteroscedasticity robust standard error for beta 1 hat is larger than the usual standard error, but it does not change the statistical significance of the estimate. Let's find answers to computer exercise 14. In part 1, estimate the equation and test the errors for AR1 serial correlation. Does it matter whether you assume wage growth and CPI growth rates are strictly exogenous? What do you conclude overall? The regression mu hat on the leg shows a negative and statistically significant estimate of rho, implying an AR1 serial correlation in the errors mu. It does not matter whether we assume the two explanatory variables are exogenous or not. They lead to the same conclusion. In part 2, obtain the Newey-West standard error for the OLS estimates in part 1, using a lag of 12. How do the Newey-West standard errors compare to the usual OLS standard errors? We estimate the model with the Newey-West standard errors and the usual OLS standard errors and compare them in a table. The Newey-West standard error for the minimum wage growth rate is much larger than the usual OLS standard error, but the opposite is true for the CPI growth rate. The statistical significance remains unchanged using either standard error. In part 3, obtain the heteroscedasticity robust standard errors for OLS and compare them with the usual standard errors and the Newey-West standard errors. Does it appear that serial correlation or heteroscedasticity is more of a problem in this application? We use the regress command and the variance-covariance matrix option to specify the heteroscedasticity robust standard errors. From the table, we find that the heteroscedasticity robust standard error for the minimum wage growth rate is close to the Newey-West standard error. The Newey-West standard error is robust to both the heteroscedasticity and the serial correlation. It implies that heteroscedasticity is the dominant problem. In part 4, use the BP test in the original equation to verify that the errors exhibit strong heteroscedasticity. The regression of squared residuals on the two explanatory variables gives an F statistic of 234 and a p-value of 0 to 4 decimal places. It suggests a strong heteroscedasticity. In part 5, add leg 1 through 12 of the minimum wage growth to the equation in part 1. Obtain the p-value for the joint f-test for legs 1 through 12 and compare it with the p-value for the heteroscedasticity robust case. How does adjusting for heteroscedasticity affect the significance of the legs? After we declare the data to be time series data, we can use the capital L dot operator for the legs. The F statistics for the joint significance of the legs 1 through 12 is 1.72 and its p-value is 0.0582. If we use the heteroscedasticity robust standard errors in the model, the F statistic for the joint significance of the 12 legs becomes larger, 4.53. The p-value becomes 0 to 4 decimal places. It suggests strong lag effects of the minimum wage growth rate. In part 6, obtain the p-value for the joint significance test in part 5 using the Newey-West approach. What do you conclude now? After using the Newey-West approach with a leg of 12, we use the test command to do the f-test. The f statistic is even higher, 7.79. The legs are jointly significant at the 1% level. In part 7, if you leave out the legs of minimum wage growth, is the estimate of the long-run propensity much different? With the legs, the long-run propensity is the sum of all the coefficients on the minimum wage variables. It is 0.198. If we leave out the legs, the estimate of the long-run propensity of minimum wage growth is just the coefficient on the variable in the current period. It is 0.151. Let's do computer exercise 15. In part 1, in table 12.1, the reported standard errors for OLS are uniformly below those of the responding standard errors for GLS, Prais-Winsten. Explain why comparing the OLS and GLS standard errors is flawed. If there is a serial correlation in the errors, the usual OLS standard errors are invalid. It is generally smaller than the true standard errors. In part 2, re-estimate the equation represented by the column labeled OLS in table 12.1 by OLS, but now find the Newey-West standard errors using a window G equals 4. How does the Newey-West standard error on the log chemical production index compare to the usual OLS standard error? How does it compare to the Prais-Winsten standard error? Make the same comparison for the after decision variable. We estimate the model by OLS, Newey-West, and Prais-Winsten. We store the results of each estimation using the estimates store command. Then we list the estimates in a table using the stab command. The Newey-West standard error on the log chemical production index is 0.65. It is larger than the usual OLS standard error, 0.48. It is similar to the Prais-Winsten standard error, 0.63. For the after decision variable, the Newey-West standard error is smaller than the usual OLS and the Prais-Winsten standard errors. In Part 3, we do Part 2 now using a window G equals 12. What happens to the standard errors on the variables when the window increases from 4 to 12? When we set the lag equals 12, the standard error for the log chemical production index becomes higher, while the standard error for the after decision variable becomes smaller. Let's complete the last computer exercise. It is about the public's view of the US president's job performance at a particular point in time. In Part 1, estimate the equation using first differencing and test the errors in the first differenced equation for AR1 serial correlation. In particular, let E hat be the OLS residuals in the first differenced estimation and regress E hat T on E hat T minus 1. Report the p-value of the test. What is the estimate of rho? We estimate the model using the first differencing method. Then we store the residuals and do the AR1 serial correlation test. There is evidence of negative and significant AR1 serial correlation in the errors at the 5% level. The p-value for the test is 0.038. The estimate of rho is minus 0.238. In Part 2, estimate the first difference equation using Prais-Winsten. How does the estimate of beta 2 compare with the OLS estimate on the first difference equation? What about its statistical significance? We use the Prais-Winsten transformation method for the AR1 serial correlation. We can store and compare the results with the OLS estimates in a table. Beta 2 is for the log gas price. The negative gas price effect becomes larger using the visible GLS than using OLS for the first difference equation. The standard error is smaller, so the gas price has a more significant effect on the approval rate using the Prais-Winsten method. In Part 3, return to estimating the first difference equation by OLS. Now obtain the Newey West standard errors using lags of 1, 4, and 8. Discuss the statistical significance of the estimate of beta 2 using each of the 3 standard errors. The standard errors becomes larger with the number of lags. The coefficient on the log gas price becomes less statistically significant as the lags become larger. Thank you so much for doing problems and computer exercises with me over the past year. I hope you have had a better understanding of the econometric concepts and ideas and have improved some model specification and identification skills and techniques. Congratulations on getting this far. Learning the methods introduced in this course is just the start of an exciting journey of your research. I wish you a bright future and good luck.